Hey everybody, more solids of revolution today. This time we're looking at volume using the washer method. So this is a situation where we have a region between curves that's being rotated to form a solid, as in this example. The region in the first quadrant, bounded by y equals x squared and y equals 2 minus x squared, is rotated about the x-axis. What's the volume of the solid formed? So we always want to start with a picture. Here it is. I've drawn the two parabolas and shaded in the region between, in the first quadrant, of course. We should also draw a typical rectangle. So a very thin rectangle of width dx and a certain height. We are going to want to imagine this rotating around the x-axis. As the whole shape rotates around the x-axis, we're going to get some big solid, which you should try and imagine, as well as some smaller shapes swept out by that rectangle. So here's the picture. The rectangle is going to sweep out a washer, and the whole shape is going to sweep out this thing that looks like it's got a funnel hole in the middle, kind of a volcano-y shape, I guess. The main thing we have to do here is to find the volume of that washer. In order to do so, we have to find the cross-sectional area. This is really a two-dimensional problem, so let's just draw that washer sort of from a top-down view, thinking about it in two dimensions. If we label the outer radius R2 and the inner radius R1, the area is going to be area of the big circle minus the area of the small circle. So pi R2 squared minus pi R1 squared. And then if we like, we can factor out the pi. The volume of that washer is just going to be that cross-sectional area times the thickness, which will be dx. So what about those radii? Well, the outer radius is going to be given by the top curve. The top curve is y equals 2 minus x squared. So at any particular x value, that's going to be the distance from that x-axis to the top curve. Similarly, the inner radius is given by y equals x squared. At any given x value, that's the distance from the x-axis to the inner part of that washer. Overall, we have a formula for the volume of that washer, cross-sectional area times thickness, as always, which is going to be given by pi r2 squared minus r1 squared dx, so area times thickness. And then let's replace r2 and r1 with the outer and inner radii, which are given by those two equations, y equals 2 minus x squared and y equals x squared. There we go. This we can simplify a little bit if we FOIL out the 2 minus x squared squared and then combine some like terms. We get that the volume of that very thin washer is given by dv equals pi times the quantity 4 minus 4x squared dx. We're almost ready to integrate. The last thing we have to do is to actually figure out where those washers start and stop. It's pretty clear that they start at x equals 0. We're told at the beginning we're only looking in the first quadrant. So we really have to find where the washers stop, and this is going to be the intersection of y equals x squared and y equals 2 minus x squared. So let's set those two equal to each other. Tiny bit of simplifying. X squared is 1, so x is 1. Again, we're only concerned with positive values of x, so we can throw away the root of that equation, x equals negative 1. Now we really are ready to integrate. The limits of integration are 0 and 1, the numbers we just determined, and dv is given by pi times 4 minus 4x squared dx. So let's factor out 4 pi. Now we have a fairly straightforward integral, 4 pi times the quantity, x minus 1/3 x cubed. Integrate from 0 to 1, plug in 1, and overall we get 8/3. Let's conclude with a quick recap of the process we used, because this is pretty universal. First of all, we sketched the region. We included a typical rectangle. This is going to help with our visualization. In particular, it's going to help us imagine what the solid and the washer are going to look like. We should sketch those two things next. I really can't stress enough. It's a good idea to draw not just the solid, but also the washer. You will get better at these sketches pretty quickly, you'll find. Next, determine the outer and inner radius of that washer. Those are going to correspond typically to the top and bottom functions that are defining the region. Then you can write out the formula for the volume of that washer. It's always going to be dv equals pi r2 squared minus r1 squared dx. It's just a question of substituting in that top radius or the outer radius and inner radius. Find the limits of integration by determining where the region begins and ends. Write an integral that only uses a single variable. Integrate and simplify. That should give you the volume.